Good morning. I'm happy to be here, and thank you to the Space Studies Institute and Heidi for having me here. I want to talk about two things that I think are essential to a deep space economy, and that is asteroid mining and growable habitats with interior landscapes. First of all, I want to briefly introduce the idea, the concept of the growable habitats, which is something that NIAC was kind enough to give us 2 grants to study. We're just at the end of our phase 2 this summer. And what I want to do is to show you some slides about, first of all, about the finished concept that we came up with. And you can see an image here that shows the fully evolved version at 1G, 224 meter radius, 2 RPM, and a precursor initial stage in the background, and behind it, the International Space Station. These are all at the same scale, just for reference. And on the right, you can see various robotic.
Can you point them with the laser?
Oh, yeah. I think I can.
That one doesn't work very well because we
Use the good laser.
Oh, the good laser. Yeah, let's see. Okay, so that is a gas station in space. And this is a robotic spacecraft that is the workhorse of this system. Here, the same spacecraft. I'm going to show you larger pictures of these later. So, anyway, this is basically a constellation of spacecraft that Joel Sossell of Transastra designed for NASA under a grant from NASA. So let's just.
The space station is the one at the upper left?
That's the International Space Station there. This is at a sort of stage 1 development of this, but I have more to say about this coming. And I have a lot of slides to get through, so please bear with me if I just take a run at this. Okay, so this is a quick rundown of the design we came up with. You can read the, can you read these?
Yes.
Are they readable? Okay, good. So I don't have to go over everything. But the important point I want to stress is that it has seemed to me absolutely essential that we find a way to build an Earth-like landscape into a habitat, or who would really want to live there, let alone raise children. So that's a big driver for me, is to try to find a way to make Earth-like environments as part of a growable habitat system. And growable because unless we start small, we're never going to build these things. You have to be able to find a way to start small so it's affordable. So moving on, I'm just going to show you a few different views of the same model. You can see that there is a river that runs through the middle. There are 12 lakes on the top of little knolls that are spaced either side of the river. Here, oh, it's the wrong pointer, isn't it? Here you can see that the 90-acre park sits on top of a 90-acre urban space that is lit through these side channels here. All of the interior lighting here comes through these side diagonal channels as a result of these intermediary ring mirrors here, which receive light from the primary mirrors that is off screen here. So the idea is we need twice as much light because you've got to light the outside for the agriculture and the inside so you have a decent environment. So a lot of light. I have over-designed this to prove that we can get more light than we really need. So we haven't done the physics and the calculations to actually tune that back, but I wanted to show that we can have enough light to do this. So, oh, and while we're here, these inclined stacks here are agriculture at the lower level, where it receives direct light from the sun sideways, and above, it's died.
No, it's still the one.
I don't see it. Oh, there it is. Okay. Above the parts that receive direct light, there are fish tanks and additional facilities at variable G, which don't receive direct sideways light. But the light for the interior goes through these slots here, and I'm going to show you how all that works. Yes?
You might get to this later, but how do you regulate the interior temperature
That's a very good question.
with all of this sunlight?
Yeah, no, it's an excellent question. And the question of how to design the radiators to take care of that is something that we're still wrestling with. Yes, it's a challenge. I think, as you'll see in some of the later slides, that the radiators probably have to be outside, on top of, or outboard of the ring mirrors, so that they get a clear enough view of the deep space. But then you have to have plumbing between the two, and it means that you've got to basically tie these ring mirrors here to the habitat structurally. They've got to be one structure. That's how I think it would go. But these are further out than we've been able to go in the 2 years that we've had grants for. But we have done some preliminary thermal analysis. It's just that I'm not the guy to talk about it, unfortunately. So, as I say, I'm going to try to keep going quickly here. So, this is without the central, that central gizmo in the middle there. That's 0G. That does not rotate. It's covered with mirrors so that the light comes in from the outside, bounces off that to light the rest of the interior. So, moving on quickly now. We built a 3D model of this. We had it printed, and I showed it at the Wall Street Journal Future of Everything Festival on about May the 6th of this year. And I'm going to show you a little footage of that now. This is the side of the central habitat pressure island. This is a quick view showing how the shield floor is designed of overlapping plates that are flexible so that they can expand as the radius changes, the curvature can change. These are all tensegrity structures. Okay, this should play. Yes, okay.
What does tensegrity mean?
Tensegrity is a system, if you have 3 sticks in a sort of spiral arrangement and 9 strings, so the sticks do not touch, that's tensegrity. And it is the most efficient way of designing any structure, proven by math, invented by my PI on phase 2, Professor Rob Skelton from Texas A&M University. It's amazing math. It's the most efficient way to build anything. We are all tensegrity structures. We have bones that are not welded to each other, and we have tendons that allow us to move and grow, and it's just nature's preferred method because it's so efficient. If you take a look, you can get a little bit of a sense of how this environment might feel because it's actually lit by real sunlight here. And my sense is that this could be a pleasant place to live. You know, you probably want to go back to Earth periodically, but not a bad way to have your home space. Okay, having introduced you to the basic concept, how can we build something like that? You must have asteroid mining, or lunar mining, or both, to have the resource industry that can build this, because this weighs a huge amount of mass, I mean, extraordinary mass. 93% of this, of the mass of this is shielding. 5 meters at maturity, which we think is just enough, but you can always have more if you can afford it. So how do we do asteroid mining? This is a quote that shows NASA's interest in this, at least from the point of view of being able to do deep space manned missions, because you can't afford to lift all the rocket fuel off the ground. It just doesn't work. Joel Sossell was one of our team members on the grant for the habitat, and his company is Transastra Corporation. I'm going to have you listen to a quick interview that he did.
Optical mining of asteroids.
Can you?
A technological breakthrough
How do we make this louder?
that turns thousands of asteroids into refueling stations for spacecraft.
But first, Joel Sossell has to see if he can actually extract vapors from an asteroid. In other words, he's trying to get water from a stone.
Here we are at the White Sands Institute at their solar furnace facility. What we're going to be doing is sunlight from the sun is going to bounce off that giant mirror back there, and it sends the rays through this giant Venetian blind, and it'll go into a parabolic reflector and focus it down into a little 4-inch circle. Now we will have asteroid simulants inside of the vacuum chamber. The sunlight will hit the simulant, and when it does, it'll be so intense that it'll break the surface of the simulant and drive vapors out of it, water, carbon dioxide. And as those vapors are driven out, it will excavate or dig holes in the asteroid crater. 3, 2, 1, open. was coming in, it's right there. So what happens is, as a highly concentrated light comes in, it breaks the surface of the material, and it heats the material. When it heats up, it lets out water vapor and carbon dioxide. The process of breaking the surface and digging holes is called spalling. As you can see, we dug a big hole. And the spall process released debris, which is all collected inside the tank.
The dream of asteroid mining is alive and well.
We think that this could be a very important transition for mankind, as we move from being a purely terrestrial species to being a spacefaring species where our industries go into space. At that point, it will be possible for people to actually go and colonize and settle in space.
Okay. This is just a quick slide showing the technical results from the experiment, and you can see that in a very short period of time they excavated, I think, about sort of approximately 6% of the mass into volatiles. Here's a quick slide that kind of recaps the process by which this happens, and it's probably worth pointing out that this whole idea of this process, the spalling process, the idea came about because people observed that there were not as many asteroids close to the sun as we expected there would be, and that something was basically deconstructing them, and it is this process, and that's what we're using, a natural process recreated in the laboratory for our purposes. The constellation of spacecraft that Joel came up with, these are illustrations I did for him on a contract basis. It's shown here, and let's see, let me just do a quick introduction of these. There is basically the gas station in its fully developed state. Here is a mining spacecraft that is designed to go and swallow an asteroid and digest it. This is a version that is for manned exploration, deep space exploration system with habitable modules attached. And this is a workhorse spaceship that can land on planetary surfaces, even on the Earth, and runs on methane and oxygen.
You say you had one that ingests an asteroid?
Yeah, we're going to get to that. Yeah, we're going to show that. So this is a quick rundown on the basis of what kind of asteroids we're actually looking for. And I just got to keep going here. This is an interesting graph that shows accessibility across the side here. Oh, sorry. So the point being that there are a bunch of asteroids that are quite close to us in terms of delta V, and that are easier to reach than the surface of the moon, and we should be looking at that as a resource to support the development of the space economy. Where are these asteroids? Basically, they're here in the near-Earth object zone, and this is a summary of a bunch of statistics that have been observed and documented, showing the asteroids that we can actually see and their relative magnitudes. This database was used by Robert Jedicke and Joel Sosel. Robert Jedicke is from the University of Hawaii, Department of Astronomy, and they built a statistical model that predicts the availability of the kind of target asteroids that we're actually interested in. Specifically, we're interested in target asteroids that have a range of size from 5 meters across to 15 meters across. We don't want anything bigger than that. And there are a very large number of them. This chart suggests, and it's a very conservative chart, that within a delta V of 2.5 kilometers per second, you can find at least 1,000 of these candidate asteroids in that category that are relatively easy to reach as they come through our backyard on a daily basis.
What does the delta V represent?
Delta V is the velocity cost of reaching a target, rendezvousing, and coming back. That's what.
Where?
Back to lunar orbit. Lunar orbit, yeah. Basically, the lunar distant retrograde orbit is where the gas tank, the gas station will be located, and all the propellant that is refined by these.
That color chart that we had a few charts ago showed the delta V changes that you need.
Yeah, okay, I just wondered where from.
Yeah.
That was the highway.
Okay, I have to stress that I'm not the guy who knows this stuff very well. I'm sort of, my knowledge is about skin deep. But I wanted to introduce this to you as a region of evolving knowledge that provides a basis for the habitat development. So I'm going to keep moving here. This is an on-the-ground controlled, laboratory controlled version of the experiment at White Sands. When you're at White Sands, you depend on there not being clouds in the sky and all sorts of variables. In the laboratory, we can control that. And this is a subject of a currently funded grant. I was in the Colorado School of Mines earlier this month and saw this apparatus that they're building for real. And it's driven by this, which is the world's largest light bulb. And they use this to run IMAX projectors and things like that. So it's a huge amount of light coming out of this. As well as investigating the spalling process in the laboratory, they're going to use the same apparatus to test this guy, which is an invention of Joel's that is basically solar thermal propulsion using sunlight, concentrated sunlight, to vaporize propellant that comes in from the pipe on the top right and exits bottom as propellant thrust.
That would only be going toward the sun, right?
No, we have, I'm coming to that, I'll show you the spacecraft design that we have mirrors that can point and collect. So.
The only reason I ask is not too many people want to go walk on the sun.
No, we can go anywhere we want. We're using the spacecraft design we have. One other point I want to cover is that there's research being done on how to handle material in zero G, because without gravity, we can separate things easily in gravity, but without gravity you need a force field of some kind. And so this is an animation I did that shows a rotary funnel in operation where you have a helical screw that drives the material and then you spin it around so the gas can escape through the center of the pipe. The pink pipe in the middle is where the gas leaves, and the rotating material exits through a port in the side and is carried out by another helical screw. This experiment is exactly that, and I believe this is going to be run in the International Space Station quite soon. It's a demonstration of that process in zero G. Here is.
Don't they do something similar when they refine uranium? Did they put it into centrifuges and
that's a similar idea, yes.
Yeah.
Yes, it is, yeah. This is, I believe, the apparatus that will fly on the space station in the near future. This is a diagram showing how that process might be put to use in space to provide bagged insulation, radiation protection, which could be wrapped around habitable space stations like you see in the bottom right, bottom left there. This is an experiment to demonstrate the optical mining part of that, the part of actually separating things. This would run on an arm outside the space station. You can see that in the middle here you would have a simulated asteroid pellet in the middle, and the aim is to break that up using sunlight, separate it out. And this is how you would do it. The doors would open and you'd deploy an inflatable Cassegrain reflector setup. The sun would be directly overhead in this, and we'd be able to, using the robot arm, keep the apparatus pointed at the sun as the space station moves through its orbit. So and then at the end, of course, you release this, close up the box. There you can see in the middle the rubble from the excavation process, and on the top there you can see a globule of water that's been extracted in the experiment.
Do you feel like there's more war coming out of this than there is for the course? I got a survey that said what were your views on this, and the major point was that they were assuming they were getting some very unusual material in the asteroid. And the question was, could they pull out enough to pay for, let's say, launch vehicles?
Well, we've done economic studies on this, and it seems to be very clear that the cost of making fuel from asteroids is significantly lower than the cost of lifting the fuel from the ground.
Well, you can have an electromagnetic gun and you can shoot your ore material out that way too.
Well, nobody's proposed doing that yet. I guess there's a reason why, but the point is to find a way to lower the cost. And this is a proposal that has been funded for a study, and that again, it's not actually my field, so I'm sort of skating across the surface here.
Okay, but it looks viable for what we're just...
Yeah, I think it does look viable, and yeah, the study that we've done for NIAC appears to show that. One of the problems is that the targets we want, which are very small, are hard to see. And there's something called synthetic tracking or digital matched filter tracking that we can use to enable. Here's how this works: is that the detector makes about 10,000 guesses in real time about which direction the asteroid could be traveling, and then it matches all those possible choices and finds the one that actually has a trace. So that you could use images taken over time and sort of superimpose them in all the possible combinations and find out where the track of the asteroid is that you can't actually see in a single frame. So this is real technology that is going to help us see these critters. Here is the first of 3 telescopes designs that have been proposed as a progressive series to implement this technology. This is the second one, which has 4 Canon telephoto lenses as its basis, and there will be 3 of these craft orbiting the Earth. And finally, this one is the sort of the granddaddy of them all, which would have the capability to track more than 7,500 asteroids per year, including 600 water-rich low delta V targets.
Question. This is actually going to be a good one for what you just showed is going to be a good section of the talk, I'm thinking. When you grab this asteroid, or I'm assuming this spacecraft is going to go around the asteroid,
I am coming to that.
capture that, do what it needs to do, right? You get all this gases and whatever. What do you do with the rock?
Well, we
How do you
think
get
that
rid of that so that you can put it into some other orbit or some other place that's going to be...
We actually want that because at least I want it because I see it as the source of radiation shielding for the habitat.
Trash is his treasure.
Okay,
Yeah, yeah.
but
Yeah,
you're only going to need so much of it, and then you're done. So what do you do with the rest of it as you start?
Well, the space habitat is going to need a very large amount of shielding. I mean, yeah, I don't know, truthfully. That's a good question, but it's not something that I know the answer to.
Okay.
Yeah. So here we come to the spacecraft that actually can capture these and use them. First of all, we would fly a very small demo of this. This is like a tiny toy version. It would come launched with its own asteroid, which you see following behind, and it would then turn around, swallow it, and just prove that you can do this maneuver, basically. The technology for bags to enclose asteroids is about TRL-4, I think, right now. We want more capability for our capture mechanism because we want to be able to rotate the asteroid inside the bag in a controlled way. And so I'm going to show you, I'll show you that in a little while. This is the constellation of spacecraft that Joel's study produced for NASA. And I'm going to go quickly through this. This is the gas station part of it. There are 2 habitable modules attached. You can see left and right, and a refinery system, a fuel processing system in the middle, and storage, cryo-storage behind the solar shield at the bottom. This is the reusable spaceship that we mentioned previously, which can also be used as, sorry, moving on here. So, this is the deployment sequence for the Lunar Orbital Outpost. And that's the refinery, the fluids refinery section. There's the reflector and a robotic arm at the bottom. This is that same set of parts adapted as a deep space exploration system. These are the mirrors that you were asking about, I think, earlier. And here is a geologist, a couple of geologists inspecting an asteroid up close. This is a little scooter spacecraft that could grab small boulders and that parks attached to the deep space exploration system. Here's our reusable spacecraft on the surface of the moon. This same constellation can be deployed at Mars, and it can land on Mars. Now we're coming to more recent work. The Honeybee, which is the spacecraft that swallows the asteroid, the first version of it, is designed to catch asteroids between 5 and 15 meters across. This shows that you can pack that inside a Falcon 9 fairing. It's not that hard, and the red elements you can see are the optical mirrors that fit inside and must be arranged inside to concentrate the sunlight. This is a that did not play. Let's see if I can click this. Oh, here we go. This shows the bag opening. The cage expanding. It's based on a geodesic, the simplest geodesic dome, the soccer ball. And it's arranged in 3 segments which can open out, enclose the target asteroid, close up again, and then you close the bag. The point of this configuration is you can see there are robotic arms inside the bag that hold the cage. And the design of this mechanism is so that they can basically manipulate the cage and turn it around in any direction, so you can bring any of the surface of that into contact with the concentrated light focus, which is right there. That's the shroud out of which comes the focused light that we saw in the previous video.
Can I ask a question about the motivation for this habitat?
Yes.
Have you seen the TV series, The Expanse?
Yes. Yes, I have.
Why is this better than having a colony inside an asteroid, like in The Expanse, or on the moon, or on Mars?
I'm not saying, I'm not going to argue whether it's better or not. I think it probably is nicer to have something where you can have a lot of sunlight inside, and you can have an environment that feels like, you know, landscape that we're used to here on Earth. I think that would be a more pleasant environment in which to live and raise kids than living inside a rock. That's just my opinion.
Is it also true you'd rather not be down in the gravity well in order to get the stuff out?
Yeah, I mean, exactly. This way you have control of your gravity, you know, effective control of the gravity, and I don't see any reason not to have that. And I think that this way you can, once you learn how to build these, and I think it's not that hard actually, it's just a matter of cost. And on the subject of cost, it's my hunch that with robotic technology, you know, we're just at the beginning of robotics right now. It's barely a couple of decades old. We have no idea quite how extensive that capability is likely to be, but I suspect that we can have a civilization where we live on the backs of a robotic slave class, in effect, that make the economy work, and that therefore this kind of
What would be
is
the
possible.
observational signature from the point of view of astronomy of such a structure in space that we could look for?
I don't know. Big mirrors for one.
And a lot of heat being radiated out?
Yes, radiated heat, electromagnetic signals. Yeah, I don't know. That's a good question. So, let's see, where are we? Okay. In order to build a habitat, you need a much bigger version of the asteroid catcher. This is what you see here. That's the Queen Bee back there. And that is designed to enclose 40-meter asteroids instead of just 10-meter asteroids. The question is it possible to launch something like that? And we figured out, we did a study, I did the study on this, as to how you could pack that inside a BFR fairing. And it can be done, and I'm going to show that to you in a minute. Let's see, here it is, in fact. Let's see if it's going to start. Yes, there we go. Okay, so first of all, and I apologize, this is not a completed animation, it's in progress. I hope to complete it next week. The reflectors at the top and bottom have not deployed. They will, in what I'm going to do, they will deploy off screen because it's simply too hard to unfold them. But this is how you might plausibly design a spacecraft that could collapse inside a BFR fairing and still swallow and digest a 40-meter asteroid. So, having laid some groundwork, conceptual groundwork on the asteroid mining side, and show that we can have a spacecraft big enough and capture enough material to plausibly build a large habitat over 25 years, I'm going to now look briefly at the costs of that. We did some cost exercises. Again, this is not my part of the grant, so I'm going to skate over the surface, ask questions, but I'll do my best. Craig Peterson, whose name you see here, who works for Joel, did the work on this. This is a quick summary of what the starting point for the costing exercise. Quick summary of the habitat concept that we came up with. So it's here for that reason, just to anchor the basis of the cost exercise. This is a very simple diagram that shows which configuration we chose to use for the habitat. We also explored sun pointing, but we found that the costs of having to turn that continually, while you could manage them at the small end, at the large end it was unmanageable. So we've ended up with a quite traditional configuration here. So what the numbers here, if you look at the bottom number, 8.489, and you look at the top number here, which is the amount of mass for the shield, you see that the shield comprises about 95% of the mass of the habitat as a whole. Here is the results of a costing exercise we did on lunar resource as a source for the material, asteroid mining as a source for the material, and bringing everything up from Earth. And for the Earth-sourced version to be competitive, it would have to be less than $100 per kilogram approximately. So we think there's a pretty strong case for using material from space. This slide I don't really want to talk about. It says at the bottom line what I just said. Now here's the part I really wanted to talk about, which is how you design a growable habitat. And that's what I spent most of the last 2 years thinking about myself. There are various elements that end up being drivers here, but two of them in particular turn out to be important, and those are the need to contain atmospheric pressure and the need to shield against radiation and grow. To combine those two with growth is enough to pretty much determine what you do. So, this is a summary in 2 slides of the conclusions that we came to, but the bottom line is that we need to have 2 separate structures. You must have a separate shield and a separate pressure hull structure, one inside the other. If you want them to grow, that's really the only way you can solve the problem. And of course, I'm just going to skip this second chart here and head on to the actual geometry issues here. And of course, the other factor is that we want to get light inside. So light, expansion, and growth, you mix those together, and you pretty much have to go in the direction we went. So because we want to keep mass under control, we want a lightweight pressure hull. And it turns out that in order to grow the pressure hull, you really need the pressure hull walls to be flexible. The analogy I would suggest to you here is that when a butterfly is emerging from a chrysalis, it has to be flexible to do what it needs to do to grow. Once it's gotten itself expanded, then it stiffens up the wings and it stiffens up all the inflatable parts of its system. And we could do the same here. I don't know exactly how that stiffening would take place. We've not explored that. But for the purposes of growth, we must have a flexible pressure hull. Also, we decided we needed to grow in large steps. In order to get economically out to 1G, we decided to have the pressure hull grow in 5-floor increments instead of a single floor at a time. So we grew in 20-meter steps. Just you can get there faster, and you can still infill afterwards the intermediate floors. Now you're starting to see how the two things fit together. You can have an opaque shield floor, that's okay, but the shield walls as well as the pressure hull walls must be transparent to get the light inside. Incidentally, you can see here we have a 3-layer structure in the shield floor, which is a sort of a water sandwich of 1 layer of water and a thin layer of asteroid material outside and a thicker layer inside. This is to get the best reduction, the best Z performance that we can in terms of radiation reduction. Again, not my field, but I believe that's the rationale for this. Incidentally, in order to keep this profile, because there's so much mass involved, you don't want to have the full shield thickness at the beginning. You want to grow it over time, as well as growing this sideways. So we needed to have a concept for a 3-layer sandwich that could grow in thickness and still maintain the relative proportions. I will briefly describe how that's done. It's done by having several layers of water bag material, layering them in the right direction, in the right order, in the right thickness, and then as you increase the thickness of regolith, you transfer the water from the outer layer to the next layer in, and then progressively, so the layer of the water migrates inwards as the shield gets thicker. That was Joel's idea, pretty ingenious. The wall, we think, we pretty much pointed towards fused quartz glass. Since it must be highly transparent, it's got to be reasonably strong, it's got to have high transparency. We looked at using water, but 5 meters of water, you lose a lot of light, and also the light gets shifted towards the blue end of the spectrum, and we don't really want that. We want a full spectrum sunlight inside. Counter-rotation, possible, we haven't looked into it. So thickness of the shield increases over time. Now we're getting to the light engineering part of it, and this turns out to be a big driver. So the conventional 45-degree mirror arrangement is what you have to do in this situation. And now we come face to face with the problem that I mentioned earlier about you want all your agriculture to be in the walls where it's not taking up floor space, but then it takes up all the light. So you've got to find a way to get light through that. You need more mirror size. Come on, here we go. Larger mirrors, and you have to angle the light into the interior, and you can do that by tilting the farming stacks so there's a slot between them for the light to get inside. Excuse me. So a lot of light comes through the shield. In fact, it comes through in 2 directions. And that does, as we shall see a little later, that drives you in a particular direction with regard to how you structure the shield.
Have you looked at electromagnetic fields as being a way of providing shielding?
We did not look very closely at that. I was aware of some NIAC work that had been done on electromagnetic shields for missions to Mars. I'm aware of that. I don't know the latest state of progress on that, but they were working quite hard to shield a fairly small container.
Well, they were looking at quadruple static systems, and it looked like it was promising. That was
Yeah. Well, I mean, obviously, if that works, it'd be terrific. You know, bring it on.
Probably brute force is better, but we are looking at alternatives.
Okay.
Water shielding is probably your easiest and best way to go right now.
Water?
Water.
Yeah, the problem is what it does to the light spectrum and the light intensity. So this is certainly a challenge that we don't have our arms completely around yet, but this is where we got to during the study. So we're now going to look at how the structure responds to the challenge of growth. There are certain things we need to do in the pressure hull to stiffen it and to enable it to have controlled expansion. And let's see, where are we?
Have you thought of using the ore itself that you've cut up, put it out there as shielding?
Yes. In fact, in the diagram that you see on the screen here, the floor of the shield, absolutely, that will be made of the slag from the refinery process. Absolutely, that's why we're not throwing it away. In
Well, the reason I'm thinking about it is when you take lead, a pound of lead in orbit to go up there, very costly.
Yeah, no, we intend to use Asteroid mining slag from the processes I showed you earlier to provide shielding for the habitat. Okay, so we can grow the shield, which is essentially a conical structure. Oh, one point here is that there's going to be two distinct growth modes. One where we're shooting for increase in the radius. We want to get to 1G as quickly as possible. And when we get there, well, while we're growing towards 1G, we're essentially growing a V-shaped valley structure. It's going to feel narrow at the base and wide further up. But when we get to 1G, we want to widen that out. And so we'll be showing ways to do exactly that. Say the initial growth will be V-shaped, and later on will grow laterally. Okay, so it's easy to grow the shield walls because they're conical, but we need a shield floor that is segmented to allow it to grow and expand. And we're going to take a look at the cross-section version here. That's the main center panel, and there is a representation of the side overlapping panels. And you can expand the lateral side panels first, then fill in the material that's needed to give them back their overlap, and then do the same for the center panel. And you can basically do this in a series of steps where you recover the lost overlap. All of that material is added inside the shield, so it's a nice thing that it's all protected work. Only the lateral glass shield walls have to be grown out in unprotected space, which will be done robotically. So now we want to move the shield walls out to make more room. That means we must have a bearing at the middle, a sleeve bearing, and so they can accept the lateral expansion, telescopic bearings. And the overlapping plate configuration of the shield floor allows us to open a doorway to bring in construction materials. And this is a very happy accident as a result of the growth mechanism for the shield floor. And so here you see we brought in new material and we built a new pressure hull floor on the floor of the shield. And it's laying there. It's been connected together. It's tied to the side walls so that it's suspended in position. And what you then do is to lower, you extend the I'm going to zoom out here. Extend the shield side walls so that you have connectivity to extend and expand the shield floor there. And now you've got your shield, your pressure hull floor is suspended in mid-space, so to speak. And you'll notice that it contains all the features of the floor above that's rotating. In other words, it has the necessary components to allow it to expand later on when it's already part of. So you build in the capability in advance of what you need. Now how the connection is made is that the shield, the floor of the pressure hull that's rotating has, let me get up to the right slide here, stowed mitral trusses in the floor of the pressure hull overhead. And these are basically, there's a channel in the floor, and there are motorized bogies that reside locked into the channel. And they have cables, reeled up cables that they can release down. So the bogies activate and counteract, they zero out the rotation of the pressure hull, so they're static with reference to the new floor panel, and then they let down cables and grasp the new floor and slowly speed it up again. So we're going to watch that in the next few steps here. You see they grab the floor, we detach from the side walls, and now the new floor can slowly be sped up by the motorized bogies in the channels overhead. And once it's synchronized, you roll down the rolled pressure hull walls, zip them together using NASA's zip pressure hull, zip airlock technology. And now you've got what you want, you pressurize, you've got what you want. And the flexible walls then allow you to do a controlled lateral expansion that looks like this. So now you have added a new floor to your pressure hull, and that's the basic trick here. That's the hard part. And although it's a little involved, you can see it's quite feasible to do. So now I'm going to start to run this fairly quickly so I can get done inside my time. One point I want to note here is that nitrogen turns out to be a significant cost factor. When you're building something that becomes a large volume, the amount of nitrogen, the accessibility of nitrogen becomes a real cost factor. Shipping it up from Earth is a major, major cost. And we would like to be able to find asteroid elsewhere. Maybe the surface of Vesta has potential for that, but this is something that would have to be worked out, you know, along the way. It would depend on how fast other capabilities move forward. So here you see the agricultural floors, which don't work when they're simply lined up straight, but once you incline them, then you can get the light inside. So this is how we're going to grow it. So I'm just going to, I think we're going to take a detour here and look at the glass walls. Yeah, so we're going to take a look at this here just for a moment. This is a diagram showing the entire growth arc of the glass shield wall from the first stage up to the last stage. And here it is at 1/10 of its final thickness, half a meter thick. And this is still very schematic in terms of structure. We know that we have to have modular construction. We know that we have to have a tensegrity cable harness to hold it all together, like the mortar that holds a brick wall together. And we know that we have to be able to replace parts as they're damaged by asteroid impact or micrometeorite impacts. So these are parameters for an engineering solution that we only see in concept at this point. So this is something this is for another day, but you can see here the highlighted section is where the radial tension hoops would be located, and they're inclined in inclined packages of cables. And it's possible to arrange reflective surfaces around it so that no loss of light occurs. The light can bounce straight between the cables without any diminishment except from the loss from reflection itself. So that's how the basic mechanism might be for the initial stage. Once you grow this out to 5 meters, you may want to use larger blocks. You absolutely want to add these from the inside. So there's a lot of sort of parameters that focus on the design problem. And again, this is still very conceptual at this point. And you see all of the light going through the structure without being lost. So having established that mechanism, I'm going to now grow this thing very quickly. Here I'm going to show you as well that the light geometry here is in orange you see these very sort of pitifully small radiators that we had in at one point, which are not adequate to the job. But here is how the light paths can grow along with the structure. And you can see in the center, we're starting to get a reflector in the middle around the zero-G engineering and research laboratory. And I'm just going to click quickly through this so we stay on target for the time. But you see the same mechanisms being used to expand the pressure hull every time, and the same sequence being repeated over and over. Once you've learned how to do this once, you can just keep doing it. And we're now starting to get a little closer to our final destination. And one more step back. And when we get up to our 225 meter radius, which is about 10 floors, now we're here, you can see that we're starting to grow in a different way. We're using the same basic concept. Instead of adding it underneath, we're adding on both sides. And you do that by building an inner wall for the airlock capability first, and then you roll up the outside wall, add your new floor, tie it on, roll down your outside window, and then do your expansion. And you can do this 3 or 4 times, and you get up to the maximum width that we can maintain without running into stability problems where we don't want to tumble along a different axis. So we can get up to approximately a hexagonal cross section. And that turns out that has a 90-acre floor space at the bottom. 90, because once we've finished growing all of the floor structure at the bottom, the living floor space, we can then add the icing on the cake, which is the tensegrity landscape surface. By the way, that Bob Skelton's research at his tensegrity laboratory has produced a piece of tensegrity code, tensegrity analysis code, that can generate a tensegrity solution for any structural problem that you feed to it, which is pretty ingenious. So we can say we want to have a landscape surface that looks like this, and it will spit out the solution in a tensegrity structure.
Now, it is not large enough to have rain, I suppose.
We want to simulate rain, absolutely. We don't know that we would have that naturally, but we would want to have a sprinkler system attached to the outside of the reflectors. So yeah, we absolutely want rain. Although it's going to travel sideways in an interesting way. And it might be more efficient to have local low-level rain generation from plumbing that's close to the ground. That might work better, I don't know. But yeah, an interesting question, absolutely. Oh, one more thing I should say is that at the bottom of each of the channels that let the light in is a shutter system, so we can have day and night. But the agricultural system works on a continual basis. So we have 2 shifts of agricultural production. It's basically we're using vertical farming techniques, so all the planting is in racks. And we arrange these racks going around each circular layer. We arrange them in a series of a zigzag format, and each zig or zag is on a pivot. And so after 12 hours, the pivots reverse, and now you have the back side is getting the light, the front side is getting in the darkness. So we have 2 12-hour shifts of agricultural production running continuously. So we don't actually shut the light off for the plant, for the agricultural part. So I have the beginnings of another animation. If you were paying close attention to what I showed you already, you would realize that even the smallest stage is quite large. And it's actually much too large to launch in a single launch. But we want to be able to start this in a single launch, and this is how I think we can do it. This is one of Jeff Bezos's New Glenn. This is a New Glenn. And so we can deploy from a New Glenn the central, and I'm just going to let this play so you can see this part is still what was deployed from the New Glenn launch. Now, the material outside, that's from Asteroid mining, being brought in robotically. All of the gray shielding is brought in robotically. And the aim is to build an enclosure with doors on either side. And you can see those. What you see added now is the beginnings of a bearing, the tensegrity bearing. The door's closing, it's getting bigger. This runs for about 2 minutes. And what we're now doing is making as large of a space on either side as possible so that we can house the bearing itself. The bearing has to be big enough to handle all the way out to 225 meters. So it's quite an elaborate piece of engineering. The orange bricks represent new material that's been brought in for the construction of the new structure. And now you're going to see the anchorage for the tensegrity bearing. And the tensegrity bearing itself. That's the magnetic interface, and this is the tensegrity cables. This will allow the structure to have a telescopic action left and right. And now we're seeing raw material being loaded through the floor so we can build the first added on pressure hull floor. And we're going to get almost to the point, now we see we're lowering down these tension cables. And we're about to add in the first added pressure membrane, which is, now we're starting to rotate. And there is the first pressure membrane, and that's as far as the animation goes. But you can see that we're going to have, in time, a full representation of the growth arc. And this is what it might look like from the outside with the Queen Bee mining ships just departing, having delivered their materials. So that's it. That's the end of my presentation.